And I think we are good to go. All right, so Brian, you can start whenever you're ready.
Okay, thank you. So I'm going to go through the BERT paper. Specifically, I'm going to look at fine-tuning. And first of all, I wanted to just briefly mention that there is a difference between fine-tuning and something called feature extraction. So with fine-tuning, you usually actually change the underlying model weights to do your either task or domain adaptation. While with feature extraction, you actually pass your data through the model without changing any weights to then get a lower dimensional representation of your data, which can then be used for a downstream task, which could be classification, right? So this is the structure of BERT. We're gonna mostly focus on fine-tuning, which is this part, but let me briefly introduce how they actually pre-train it. So they use two tasks. They use the language modeling task and the net sentence prediction task. So with the mass language modeling, essentially all that means is that they have a sentence, which could be n amount of tokens, and they mask, literally with a masking token, about 15% of the tokens or the words. And they ask BERT to try and predict this mask. The other one is net sentence prediction, which I'm not going to touch too much on at the moment, but it's essentially you have your first sentence and you're trying to predict whether the net sentence is the net sentence or is just from somewhere randomly from the document. Okay. And as you can see, is there a question? No? Okay. As you can see, there's quite a lot of tokens like CLS, SCP, mask. So what do they all mean? Because it comes up quite a lot in BERT specifically. So CLS is always a token that you add at the start of your input and stands for classification. SCP stands for separation, and you always put it at the end and also in between sentences, so here. And padding is something that you add to basically pad your input to a dimension of about 512. And that's usually represented as a 0, your input. And then mask, it's whenever you're trying to predict that particular token. So let's give a very simple example on how you would pass the data through the network. So let's say you're just trying to do a simple classification task. You would load BERT in memory where your output, you have to specify this, your output, you're not looking at all the outputs, but just at the classification output. And let's say you're trying to do something simple like binary classification. You have your sentence input, which goes through the network, and then you're looking at the class label. And that's actually why you have a CLS token here. It's always reserved for the classification. Now, when you're loading BERT, since you're doing binary classification, you have to change the embedding on the output from a dimension of 768 to just the size of 1, right? So you have to specify this. And then you would usually fine-tune it with something like binary cost entropy. So let's go quickly through a code example on how it would look like in code. So this is purely fine-tuning. So your model has already been pre-trained and you want to fine-tune it. You have something like a data loader, which loads in memory samples. So let's, for example, just have one sample, so just one sentence. You would have your IDs, your mask, your token type IDs, and your targets. Now, why is this broken up with so many different inputs? The reason is that for every sentence, so here, you have to do something called tokenization, okay? And this is quite important for BERT because it basically turns this sentence, which is just something that only us humans can read, to something that the machine can read. So the IDs is the tokenized input. The mask is something called the attention mask, which represents where in the input you have a useful token and where in the input you just have padding, so just zeros. And the token type IDs, I'm going to touch on this later, on what it is. And then the targets, which is just, if you're doing binary cross entropy, it's just going to be either a 0 or a 1, right? So you have this input. You then load it into memory if you're using PyTorch. And then you pass the IDs, the mask, and then the token type IDs to the model. The model will then do its thing and get the output. You then take the output and then you do the loss, you calculate the loss between the target and the output, in this case, binary cross entropy with loss logits. And then you do your backward step, right? And this fine tunes the model. Now, I mentioned that tokenization is quite important. So let me go through a specific case. Like, for example, you have a sentence, which is, I like to draw. In PyTorch, you would pass this through something called a tokenizer using encoder plus, and this turns it to the kind of input that BERT needs to do the processing. So the input IDs, as you can see, it's all numbers. So for example, okay, 101 is, as I mentioned, the CLS token. And then at the end, you have 102, which is your separation token. And in between, you have the vocabulary ID equivalent of your particular token. So in your vocabulary, usually with BERT is 30,000 different words. So I would be represented as 146, and then LITE to 1,000, so on. Now, as I mentioned, I wanted to go back to the token type IDs. So this is reserved to when you have two sentences. So let's say you have sentence 1, which is I like to draw, and then sentence 2, like I lied because I'm in engineering. Then you would pass this through encoder plus, which is this one. And as you can see, you have token type IDs, which are both zeros and ones. So zeros represent the first sentence, and then the second sentence is represented as ones. And then the attention mask, it's going to be all ones because there's no padding in this particular case. So yeah, just as a quick recap, you would pass this input through to get either a 0 or 1. And then you have like padding at the end to make it the size of 512. So what other methods can you use to fine tune? Well, for example, you can do sentence comparison. So for example, to see whether two sentences are semantically equivalent. So for example, with Quora, to see whether two questions are the same. So you have sentence 1 and then sentence 2, and you class label whether they're the same or not. You also have, for example, something like question answering, right? So you have you pass your question and your paragraph, and you're trying to indicate in your reference text where there is an answer, right? So in this case, it would completely ignore your classification token, although you still include the CLS token, the input, you would ignore the output and just focus on this output. Another thing you can do is, for example, tagging task. So for each token, you're trying to classify it, whether it belongs to something or something else. For example, your first token could be People Magazine, which is a publisher, right? Then Prince William, which is a person. And you're trying to classify maybe each one of these tokens to something. Okay, so BERT as a model is quite large. I think you're able to fit it on 32 gigs of memory, but there's been a lot of interest to try and shrink this down so that you can maybe put it onto embedded applications or your phone directly. So a recent development is something like DistilBERT, which essentially shrinks BERT to 6 layers instead of 12, and then trains it with knowledge distillation. And essentially this allows this smaller BERT to retain 97% of the language understanding, and it's 60% faster at inference, whilst also retaining 40% fewer parameters. And this is one of the smallest ones out there, which you can just use straight away in PyTorch. I also wanted to briefly talk about BERT, which is this type that you're trying to shrink the model in various ways. And the paper itself is a bit confusing, but they do 3 types of things to shrink the model and improve the performance. So one of them is quite counterintuitive. It's called parameter sharing, but essentially in each encoder layer with BERT, you have unique parameters, right? But Albert comes along and says, okay, I'm gonna train BERT, but then I'm gonna take the first layer and then just copy it across all other layers so that you have exactly the same parameters for all layers. And maybe in a discussion, we can go and discuss the implications of this, but essentially it does suffer a little bit with the classification task or the downstream task, but they're then able to actually scale this further, especially with the hidden units, so that overall it actually performs better than BERT with using less unique parameters. And a way that they also improve the pre-training task is that instead of using NSP, they use something else. But with BERT, originally, the NSP task is that you basically have your sentence A, and then you're trying to say whether sentence B is right or wrong. It should follow like this sentence, right? So in this case, it just doesn't make any sense. So BERT would say that it's not the next sentence. But this particular sentence B, they choose it from like randomly from the document, okay? It's, so when it comes to actually, wait, hang on. Oh no, okay. Oh, hang on, my slides didn't load. Can you still see?
Yes.
Yeah, I don't know what's wrong with my.
You may want to try to go out of full screen and reload. That sometimes helps. Yeah.
Okay, let me just reload them.
While we're waiting for Brian, I think this is a good point that a couple of us have asked questions. So Jaching and Kushal are both from the actual presenters team, if I'm not wrong. And they're asking questions to help all of us understand. So I'd also like you to, you know, ask these questions on Slack, since that is the easiest way we can have a record of things, so it's there. But if you're reading the things on the chat, it's good to try to think about on your own, and we can have a discussion after Brian's done with his presentation, right? So Jaching asked, to what extent can we use the CLS token as a sentence representation other than for classification? And then Kushal also asked, do you add a task-specific output layer? So these are, I think, you know, basic questions that we should all know about BERT. So we can get to those after Brian finishes his presentation.
Okay, great. Okay. Let's see if I'm able to again. Okay. So we touched on this. Right, so basically Albert comes along and says, instead of just choosing sentence B randomly from the document, I'm always gonna choose 2 sentences that are next to each other. And then, so if they're next to each other, this is a correct order. And then if I swap them around, that's going to be not the correct order, right? And we use these 2 to do SOP instead of NSP with your pre-training. And then they also introduce this idea of parameter factorization, which, to be honest, I couldn't really work like how it actually works in code. But what from I understood, it could be some form of matrix factorization, where they basically break up the number of tokens times the hidden layer size to 2 different matrices, where you have an embedding in the middle. And then that's able somehow to make the model smaller, but I couldn't really quite figure out how it actually would work or whether it actually makes it smaller. So maybe in a discussion, we can go through this as well. But yeah, overall, they're able to basically, with the same amount of parameters, able to achieve a lot better performance on all the other classification tasks. So one of the big problems with BERT is that it's not really good for natural language generation. And this has been kind of like investigated in papers in the past maybe year or so to try and actually make it so that it's actually good at that. But for the time being, models like GPT are still a lot better because they're autoregressive models. And we're gonna go through this in the next presentation. So is there any questions?
Yes. Thanks, Brian, for your presentation. So I have some basic questions in addition to the chat box. The first question of mine is that you have introduced lots of fine-tuning methods in BERT. And my question is that every time when you meet a new downstream task, you need to use all of these fine-tuning methods?
Whenever you're doing a new downstream task, it really depends. So if we go back to, so it's a model that will learn the task for you when you're fine-tuning, right?
Yeah.
So it really depends how you're structuring the task. So yeah, it really depends on what you're using. But yeah, you should be able
some
to
examples.
do it. Well, I gave you, like for example, yeah, here's sentence comparison, right? So if you want to compare two sentences to one another, you would just structure it this way.
Yeah.
Right.
Okay. So when you compare two sentences, you also formulate it as a classification program?
You can, yeah.
Or
yeah.
Yeah, so both the SOP task and the SMP task belong to the classification programs.
So in that case, it would be in an unsupervised way, right? So in that case, you would still have like a class label, but you've generated that yourself, if it makes sense. So with SOP, you basically have two sentences, right?
Yeah.
And you're generating yourself whether that should be a positive sample or a negative sample, depending on which order you put them around.
Yeah.
Right?
So
that's purely unsupervised.
Okay. So one more question. Why do the first task you talk about the classification, and the second one you said that we need to classify each tokens. I don't understand why we should classify each tokens. What's the difference between classification for the whole sentence or for each tokens?
So is this with the pre-training?
Fine-tuning methods, the second fine-tuning method.
The second fine-tuning methods. What, this one?
Oh.
No, so you mentioned what is the difference between the individual token and the sentence?
Yeah.
Yeah, so that is quite relevant for the pre-training. So whenever you're looking at the single like token, you're basically just looking at how each word compares to the other, right?
Yes.
While with the sentence, you're trying to build some coherence, right? You're trying to say, okay, one sentence then leads to the next, right? And you want to make sure that the BERT model understands that. And if you don't do that, then it's not going to be very good at understanding the coherence of the paragraph.
Thanks for your answers. So you can have a look at the chat box. There are two questions.
Okay, so that's great. Maybe we can discuss those two questions. I mean, I think Yifan tried to broadcast it a little bit as well. So first, let's thank Brian for his presentation.
Thank you.
And now let's all talk about those questions that came up. So Anyone want to ask their own question or perhaps add a little bit of discussion about the CLS token
Yeah.
or,
I have
how
a question.
yeah, Dev, go ahead.
Yeah, so I just wanted to know like what different types of so you have mentioned sentence comparison as a fine-tuning objective. Also, Albert is using sentence order prediction as a fine-tuning objective. So is there a distinction between, can we say that some fine-tuning objectives are very task specific and some are not? So to my understanding, sentence comparison is a very task specific fine-tuning, where, as you mentioned, if you can go to that slide, you mentioned it's for the tasks like MNLI and maybe semantic similarity tasks.
Is it one of these ones?
Yeah, this one. So I
Yeah.
think sentence comparison, when we talk about sentence comparison, it's a very task specific fine-tuning.
Yeah.
Whereas sentence order prediction is more of a task agnostic, because it's somehow about capturing the discourse of two sentences, which comes first in a natural language. So am I right in thinking that, like, some
yeah, you're right.
Metrics like sentence order is task independent?
Yeah, you can do that either for your particular problem that you're trying to solve, or just for the natural understanding. Yeah.
Okay, so something like sentence order is something we can always do irrespective of the task when we're using a transformer, right?
Yeah, it's been shown that you want to do something like SOP whenever you're pre-training to make sure that BERT actually understands the coherence, gets the coherence right. Yeah.
Okay. Yeah.
So I think we can add a little bit of discussion towards that. I mean, when we think about the key task that BERT started us with, which is the next sentence prediction as well as classification, I think some of the other models that we've seen eschew from the next sentence prediction. Right? They don't find it helpful for the model to learn jointly for the second task. So there are good reasons to not have it in there and just work on classification. If you think, for example, your task doesn't require this course understanding or is less dependent on it, you may decide not to have that as part of the model. And of course, that can save with the parameter size, so some shrinkage of the parameters can be done that way. So you can think of it also as a form of regularization or a multitask learning, right? So doing all of these different tasks are somehow making the model more robust to seeing a new data set or a new set of examples that it's not been specifically trained for. But we have to make sure that the batch of tasks that it has been trained for are useful generalizations for the task. Right, so I think Dev's point is really nice in the sense that if you think your tasks are domain dependent, maybe something like a classification won't work well without a lot of fine tuning. But if your task is somewhat agnostic to the domain and has to do with more discourse, then perhaps paying more attention or more weight to things that have to do with coherence, like next sentence prediction, or even you could introduce the next sentence prediction or something like that, could actually be helpful, right? So those are very important things to do. Yeah. Other comments, please.
Hi. Can you hear me?
Yes, we can hear you.
Yeah, I wanted to discuss about the fact that Albert, despite its smaller number of parameters, has a better performance than BERT, right? So I haven't read the Albert paper. I suppose it's something like, it is maybe because BERT is doing some sort of sophisticated overfitting of the data set, but maybe there are some other insights in the paper or of why this happens?
So with Albert, when they do this, Albert actually on his own doesn't perform better than BERT just by parameter sharing. It's the idea that because they're able to compress the model. They're then able to scale it back up. And because it's a lot larger than the original one, is able to then perform better than the original BERT. That's roughly what I understood from it.
But in total, you've got less parameters, right?
Okay, so I think what they mean here is unique parameters, because you see how it's parameter sharing. I think deep down is actually still like more parameters than the original BERT. But this is not something that I'm entirely sure. It's something that they don't make very clear in the paper. And I would say it's probably one of the critiques.
Okay, so this is a good point. So other people in our group have actually read this paper in a bit more detail. So I invite any of the group members in Wing, especially those of you who've actually used some of these systems. Maybe if you remember the details, you can also help to clarify. It's also, you know, if you want to read the paper right now, there's a link that is just copied from the list of papers that Brian and everyone else put up there. So I invite you to actually look at the paper now and take a look. So most of this information is on page 4. I'm looking at the paper now to try to decipher it as well.
I think I remember one part, it did an optimization in the input part where there's this embedding layer, and it did some kind of projection to a low dimensional space first, instead of tying the input embedding to the hidden size. So
right.
I think when it's talking about base, large, and XL and double XL, maybe it's varying that projection size, which will effectively change the amount of parameters in that particular factorization. So your slide also mentions parameter factorization, right? So it's
here.
It's the input part, I guess.
Mm.
It maps the embedding of the each token into a low dimensional space and then projects it to the hidden space.
Okay, yeah. So in this case, the embedding, they always keep it at 128. Yeah. Compared to BERT,
this is a good matrix
factorization
approach that you can take in a lot of different ways when you have fairly sparse matrices and you want to densify them, right? Is to do a low dimensional approximation using a lossy or complete preservation matrix factorization. They're doing it on embedding like Dev and Brian mentioned, right? And then there's this other thing that Brian mentioned, which is the cross-layer parameter sharing, right? That's right in the section after that.
This one?
I think when you were talking about the cross-layer parameter sharing, right?
Oh, this one.
Yeah, there.
What about it?
So you said it shares parameters across all layers, right? So yeah, that's also a pretty interesting observation that they've made. That's a little bit counterintuitive, like you said. I mean, generally what we think is that sequential layers manufacture deeper and deeper semantics, if we can say. I use semantics very carefully because I think a lot of people believe that word embeddings actually, and you know, BERT does preserve semantics. It doesn't. It preserves you know, statistical useful collocation and frequencies. So it doesn't actually understand anything. It just has those irregularities encoded. So, I mean, if you look at a lot of people in AI, they're really worried about the hype that gets out around GPT, which I guess we're going to get to soon as well. Yeah. So here they said that they share all the parameters. So, you know, when we think about having different layers, each layer is supposed to encode something a little bit deeper, right? From the single words context to having a larger context window, moving from single words to phrases, and then other types of relations. So here, they said that they're actually sharing parameters at all levels. It's not really clear exactly what they're sharing, But you know, maybe those of you who've read the paper more, maybe you guys can clarify as well.
So from what I understood, it's the first layer. So they learn BERT, and then they just take the first layer and then they propagate it, from what I understood. And the parameters in the first one would be the same ones across all the encoder layers.
Yeah, here I have a question that because when we use a very shallow level, maybe we can extract some generalized features, but if we use the parameters of the encoder 1 for all 12 encoder, I guess maybe we can't extract more semantic features in the higher level. So I don't know why it works.
Right, exactly. Like usually with vision models, the lower layers encode things like lines, like very, very simple lines. And as you go up, you start encoding things like shapes, like squares, triangles, whatever. And then the top layers are like class specific.
Yeah.
So eyes, tires, you know, arms and legs, whatever. So with vision, it's intuitive, but here they've at least shown that if you just take the first encoder layer and just propagate it, it actually doesn't break the model. Like it doesn't make it better, but it doesn't completely break it. I think it suffers only about 3% points. So it's 3 percentile points lower in prediction than BERT.
So anyone want to hazard a reason why that's the case? I mean, this is a bit of a stretch, but if you remember, maybe, yeah. Alex?
Yeah, I think that there is probably, so that's what I was mentioning earlier, that I believe that maybe BERT is doing some sophisticated overfitting of their data set and all the very large models as well, even if they have a gigantic input training data set. So there might be wiggle room in each layer to be able to both capture the low-level feature, the low-level regularity and the higher-level abstractions. And at the same time, sharing the parameters allows to additionally benefit from the recursively similar structures, because we're talking about language, and you might capture things such as how elements which are on the left relate in that manner to elements which are on the right. And this could be at various levels when you look at the word level, but also at the sentence level or at a bit more distant neighbors. And so if there is enough power in one layer to, or enough, I would say, yes, enough capacity in one layer to both capture the low level features and the higher level features, doing parameter sharing with the low for reducing the number of parameters, capturing both the low level and high level features, but also benefit from regularity at various levels of abstraction. So that's a very generic way of describing it. I'm not sure if it was clear, but yeah.
Okay.
Yeah, very good. So I've also pasted in both Slack and chat a paper that I think many of you may have read that tells a little bit more about how to introspect BERT. I think a lot of us have this problem that we understand the map, but we don't have much intuition for why the thing actually works. So this is a nice paper. I think maybe we've actually gone over it this round, but definitely before in 6101 about what does the BERT learn. So it tends to learn a lot of positional information. There's quite a lot of redundant information in BERT, even when they look at what is being encoded. So parameter sharing may not hurt so much there. And even at multiple levels, it is encoding very similar information. So perhaps that's why, repeating the parameters at sharing all of the parameters at multiple layers doesn't hurt as much. Okay, great. So anyone want to discuss any more about Albert and BERT? There are definitely a lot of ways that people in NLP can make impact on studying embeddings and architectures for pre-training. So this is an important topic, yes.
Yeah, with respect to what you posted on Slack, right? That particular paragraph from the paper. I mean, usually in NLP, you do this, right? Like you take a vocabulary, project it into a smaller embedding space. You assume the embedding space that you project into is smaller than the hidden dimension. So why is it any different from the normal way? Like, how are you saving the number of parameters here? This is what usually happens, right?
Is it what is usually happening? You mean how we treat embeddings in the first place anyways?
Yeah, I mean, what's the innovative part in it? When H is much greater than E, yeah, sure, this makes parameter savings, but that's usually the case. Embedding space is 150 or 200, and then H is usually 1024 or 512 or whatever that is. So where is the parameter number of parameters being saved here? Maybe it was a wrong design choice in BERT to make E is equal to H, and they fix it in this.
Yeah,
I'm
exactly.
not sure. Yeah, when I'm reading this paper, it looks like this is just a standard embedding approach. So I'm not sure. I mean, if you're decomposing V times H and then representing it with a lower rank, two lower rank matrices where you have a fixed dimension of size E, that is the standard way you do matrix factorization anyways. I was reading it slightly differently, but if anyone has a clue exactly what they did, that would be helpful. I thought they were just looking at the vocabulary size of 30,000 and not the larger vocabulary size. I'm saying restricting to this 30,000 dimensions that is in the vocabulary of BERT, we further decompose it again using matrix factorization, but maybe I don't have that right either.
No, I think it's just correcting the mistake of BERT, that is setting the learnable dimension of each word embedding. It was set as to be similar to the hidden layer size. So they're just scaling that down to a more manageable size and then projecting it back to a higher dimension. And then these two factorized states have much more lesser parameters than when you would have a V cross H embedding matrix. So it's just really creating a V cross 300 or V cross 128 dimensional embedding matrix and then projecting it back to a higher dimension.
Yeah. Okay.
Any other questions? So, okay, why don't we go on? You know, I want everyone to save their energy for the rest of the presentations too. Let's again thank Brian for his presentation, and we'll go, move on to the next one.
Thank you.
Hi all. I'm going to be presenting about GPT. I'm a little nervous now after the the warning about hyping up GPT too much. So I will try to avoid that. Let me just share my slides. Okay, can everyone see? Yeah. Percent. Okay, there we go. All right, you guys can see it, right? It looks good. Yes. Okay, awesome. Well, hi all. My name's Khush. I'm going to be presenting about the GPT family of autoregressive language models. This is actually my last week with the seminar because next week I'm going to be enlisting in the army. So yeah, exciting times. This is what I hope to cover. So first, we'll explore how humans learn to perform certain tasks using natural language. We'll take a look at how existing pre-training methods and approaches fall short. We'll touch on a couple points that were mentioned during the discussion of Brian's presentation. Right, and then with those in mind, we can finally get into the GPT family. Right, so we'll look at the evolution from 1 to 3. And then, we'll look at what it's good at, what it's bad at, and implications, further improvement, and so on. So we'll begin with the following question. So how do humans learn to perform a task? We always have to be careful, of course, not to overgeneralize, but it's useful to establish a model later on for our discussion. So we'll take the example of an Amazon Turk worker, right, who, is effectively just their knowledge and understanding is a commodity. in the like truest sense of the form, much as the knowledge and understanding of a model might be. Right, so the MTurk worker will come with some set of experience, knowledge, and crucially some pre-existing understanding of natural language. So initially, we present the MTurk worker with a task. It's given some article. Does it talk about satay? Now, this may superficially seem like a straightforward instruction. However, it is somewhat ambiguous in that what does it mean to talk about satay? Right? Is a single mention enough? Or does the whole focus of the article need to be about satay? And so to help resolve those ambiguities, we then provide the MTurk worker with an example or two. Right? So we'll provide an article, and then we'll provide the ground truth. So does this talk about satay? No, it does not. It's like Latin boilerplate. So generally, what's happening here is that the agent begins with some understanding of natural language, and implicitly we assume that that means they have some understanding of the world and some set of skills, etc. They're presented with a task, and then in order to learn to perform the task, the agent is provided a few examples. Right. So now let's move on to the two approaches to pre-training. So the first would be when the pre-training and fine-tuning objectives are the same, right? So I gave the example here of if you were to pre-train on Squad and then fine-tune on a custom Q&A dataset in order to build a Q&A model for, I don't know, let's say a corporate knowledge base. Right, the other approach would be the one that Brian just spent a little while presenting. Right, so this would be the BERT approach when you have in a different upstream and downstream cases. Right, but generally they share the same sort of ethos, which is that you begin trying to acquire some general understanding of language, and then you apply that to some task with which doesn't have that much training data. Now that's well and swell. Where do these fall short? So with the left-hand side, the Squad approach, I think its primary weakness is that it has a very narrow scope of application. Right? Your task which you're training, you must have a large data set to fine-tune on. And then because the implicit assumption is that you wish to, to pre-train on, because then you wish to fine-tune on a narrow subset of that task. Right, so that's one limitation specific to that. One limitation of the BERT approach specifically is the pre-train fine-tune mismatch. So this was actually talked about in the ExcelNet paper, where they say that because there's a mismatch in terms of the objectives during pre-training and fine-tuning, BERT's performance suffers. And so what ExcelNet tried to do was to remedy that by adopting an autoregressive objective as actually GPT did. So generally we can say that these two share three weaknesses. The first is that their need for labeled examples limits their usefulness. Right? They generalize poorly. Now I think that this point about poor generalization links to something that Alex was mentioning earlier when he talked about BERT overfitting. Right? So when you have a very powerful expressive model and you then try to train it on a very narrow distribution, it's almost a foregone conclusion that it will end up overfitting in some way. Right, and therefore, learn superficial relationships which don't capture what we're trying to learn. And the final weakness, since the title of this presentation is human fine-tuning, is that humans don't need data sets. You need one or two examples, not like 1,000 or whatever. So now that we've done that, we can finally start digging into the GPT family. So for those of you who don't know, GPT stands for generative pre-training, because that is the kind of like quote-unquote special approach here. And so these are a collection of autoregressive language models, which became famous in part, I think, because of GPT-3 and its ability to, somehow do everything under the sun, quote unquote. So they are the three models, and we're going to go through each one and look at how the model evolves. So we'll begin with the first one. So one thing I really like about the GPT papers is that the titles sort of capture the core insight of the paper. So the core insight of the first GPT paper is that generative pre-training works, right? That is pre-training with a generative objective. For example, the autoregressive language modeling objective, which they used, works really well, particularly when you use a transformer-based architecture like they did. Right, so, okay, there we go. Yeah, so you can break the training up into two phases. Right, so the first is the unsupervised pre-training. But so you're trying to optimize the this equation right here, right? So where this funny U is the collection of all tokens in the corpus, right? You're essentially trying to maximize. Okay, so what's the probability of UI given the preceding K tokens and parameter theta? This is a very this is fairly standard. It's this part of it, this part of the training unsupervised. The other bit is supervised, right? So this is when you have some minor architectural variations and input transformations. So if you want to get a sense of what that looks like, just consult figure 1 here. So on the left, we have a look at the architecture. So essentially, this is just the BERT decoder bit. Oh, sorry, I shouldn't say BERT, the transformer decoder, and it's just stacked on top of each other 12 times. And then on the right here, you get a sense of both what the minor architectural variations might look like and how the input transformations work. So we'll just we'll zoom in on I think the classification one, since that's just the simplest. Right, so you have a start indicator, the actual text itself, and then the extract, which indicates like in the end of the input sequence, and then that goes to a transformer and then a linear. So although the architecture itself is generally task agnostic, they do still slap on these linear layers at the end to adapt it for each task. Right, and obviously note that as we've talked about, fine tuning does include weight updates. So one question I had when I read about this is, why is it effective? It's a lot like when you read about for example, the word2vec, right, wherein you have a seemingly simple training process which appears to be quite effective. But so the paper presented the hypothesis that the underlying model learns to perform many of the tasks that are later evaluated on in order, as sub goal, in order to improve its language modeling. Right, so we'll talk a little bit more about that discussion during our discussion of meta learning. Right, and just an aside, you can refer to the ablation studies for some empirical support that transformers are better than LSTMs for this purpose, and obviously that pre-training is better than no pre-training. So this is what I like to call the Jammu spectrum, right? So on here we have a computer. I probably shouldn't have put HAL 9000 because that's in 2001 Space Odyssey, that's quite a smart computer. But we'll just pretend this is a dumb computer on one end, and on the other end we have a very intelligent human. So GPT-1 is towards the left-hand side, right? It's largely task agnostic, which is great, and yet it falls short. It doesn't understand language that well. Now let's move on to the second one, to GPT-2. So GPT-2's big insight is that, big change I should say, is that it became wholly unsupervised. So all training became zero shot. There were no weight updates during fine-tuning, and indeed there was no concept of fine-tuning at all. You would pre-train the model is much larger than GPT-1. You'd pre-train and then go into your evaluation. So I think here's where the idea of input transformations was really developed, in that now previously you had minor architectural variations. Now all architectural variations are gone. Right? Language itself, I put a little quote here which I think encapsulates the author's philosophy. Like, language itself specifies everything. Right? And just a quick aside as to the inputs themselves, they use byte pair encoding. I just thought in the event you wish to know. Right? Yeah, it has a good balance between character and word level language modeling. Right? And it can also, to some extent, take into account morphological information. So, oh yeah, wait, I wanted to mention, earlier, Professor Min talked a little bit about how when you're trying to adapt a model to a very specialized task, which may be outside the domain of the pre-training, you have to do quite a bit of fine-tuning, right, as one might expect. One thing which the GPT-2 and/or 3 paper posited is that would not be the case, because all NLP tasks, in their eyes, could be formulated as autocompletion tasks. Right, so one example might be you give it a question and then an answer, right? So you say then the question, you do question colon whatever it is, answer colon, and then it's expected to, taking into account the preceding question, the preceding text, answer the question. right? And so therefore the global minimum of the pre-training objective is in theory the same as the global minimum of the fine-tuning objectives, right? So at least in a toy setting, and that was something which, so the problem then becomes, how do you practically achieve that? And so that's something the GPT paper explored, right? So on our this Jammu spectrum, the GPT-2 paper is slightly closer to humans, but you don't need to fiddle a lot with the architecture. And so in that sense, it's more robust. It's slightly more generalized. You require no training data during fine tuning. And finally, instructions are structured with language. Now we're going to look at the third and sort of combination of the GPT models, and it's in that context which we'll discuss and analyze the results and their implications. So the first thing to note about this model is that it's gigantic. I don't know if you can see here, there's a tiny G over here, and there's a humongous G. So this is a 2-scale representation of how much bigger the GPT-3 is compared to GPT-2. Right, so it has 175 billion parameters, right? Whereas GPT-2 only had, I think it was 1.3 billion. So GPT-3 makes extensive use of what's known as in-context learning, right? So we use the text input of the pre-trained language model in order to specify the task, right? And so at inference time, the model is conditioned on a certain context, which includes both instructions and some set of examples, depending on the situation, all in natural language. So concretely, we can get a sense of what this looks like by looking at the following figure. So there are 3 settings that were explored for in-context learning. The first is zero shot, wherein there is just a task description and then the prompt. And so the language model is expected to complete. Right, so the other one would be, the second one would be one shot, wherein there's a single example. And then there's few shot when there are multiple examples, or as many as will fit into the context window. Right, you can contrast this pretty sharply with traditional fine-tuning, right, which is, as they note here quite clearly, it's not used for GPT-3. Right, so just like GPT-2, there are no weight updates occurring at all. Right, so all learning is quote-unquote in-context learning. Right. Now, I just want to quickly note for zero shot. Right, so zero shot is challenging. I think this is the most challenging of the 3 settings, for the simple reason that often the task description is ambiguous. Imagine being asked to make a table of world records for the 200-meter dash. Right, now that is an ambiguous directive in that it's unclear what the format of the table should be and what it should include. Right? However, I think that they decided to evaluate it anyway, just because zero shot is very close to certain tasks such as translation. Now let's do let's have a quick summary of the results if you don't want to spend too much time on this. But so GPT-3, it goes without saying, it's really good at language modeling, as you would expect. It was trained on 300 billion words or something mental like that. It does very well on common sense reasoning, generative tasks, e.g. Writing a news article, Winograd style tasks. So these would include, for example, I don't think that's very clear. Let's say there's certain sentences where the pronouns are grammatically ambiguous, but as a human, they're semantically unambiguous. Right. So for example, let's say you had the judges huddled in the building while the protesters were were outside. They were really scared. Grammatically, it's ambiguous what they refers to, but from a semantics perspective, we know that they refers to the judges, since there's no reason for the protesters to be scared. It's not that great. So returning to this, GPT-3 is not that great on tasks that involve comparing 2 sentences or translation tasks, for reasons which we are going to explore when we look at the shortcomings. But aside from, I suppose, the more formal tests, what I found most interesting is that GPT-3 seems to be weirdly good at several qualitative and synthetic tests, and that this is not reflected in its performance on various benchmarks. Right? So I think the most obvious one to begin with is the news article generation. Right, so one important thing to note right at the outset is that so the way this worked is that they selected titles and subtitles from various news articles online, and then GPT-3 was asked to write the actual article itself. So the articles were not in the training data, right? And crucially, model outputs were formatted and selected entirely programmatically, so as to avoid human cherry picking, right? And even with all that, humans did just barely better than chance in terms of distinguishing between wait, sorry, give me a second. Between generated and quote unquote real news articles, right? Which I think, hats off to GPT. Like, some of its articles are obviously garbage, as one would expect. But I think the fact like this, yeah, I'll leave you guys with that. The second one was its ability to learn how to use novel words, right? So given some example as context, he was able to learn how to use, fardoodle, yalu balu. And as you can see here, so the authors claim this is a representative set of completions. As you can see here, with the exception of this one, I thought this one was slightly awkward. It seems to be performing fairly well, right? And so if we take a look at this little spectrum, we can see here our little mTurk worker is starting to get, slightly worried, right? So GPT-3 is much closer, in my opinion, to humans, because it can generate fairly realistic prose, right? As we explored previously, humans are unable to distinguish. It gets decently impressive results on various benchmarks. And it can apparently write code, right? So I think this hints more to the broader phenomenon that GPT-3 has been able to do a bunch of crazy things, like, for example, generate React code, which we otherwise wouldn't have expected it to be able to do. Now that leads me to the question, why? Why? Like, why does GPT-3 work? Right? Like, if you stop and think about it for a little while, it's crazy. What you have is a model being trained on what is essentially a very stupid training objective, and yet it's able to generate working React code, right? Which, I mean, that's impressive. All right. Now, we previously touched on the idea that the model may be learning to perform these tasks in order to achieve its language modeling, improve its language modeling. And so now we're going to develop that idea using the concept of meta learning. So this is really like the kind of climax of this presentation. So with meta learning, it's what it says on the tin, right? The model learns to learn, right? Like meta learning. Right? Specifically, during training time, it develops a broad set of skills, which then it can then use at inference time to rapidly adapt to the task at hand. Right? So we can see what this might look like using this figure here. So on the top, this purple arrow, we have we have the pre-training going on during this is a forward pass. So this is what they described as the outer loop. Now, within that, it learns several different skills, right? So it learns, there's the examples here. There's addition. This is letter unscrambling, which, by the way, is another synthetic test GPT-3 performed decently well on. And translation, which, by the way, it did not perform well on. And so you can see how in its attempt to get better at language modeling, it learns all these different skills. But I hear what you're thinking. That sounds very speculative. So let's look at a concrete example. Oh, wait, okay. First, let's talk about this. This is the hypothesis which this embodies, right? So it holds that neural networks possibly function as an ensemble of many different subnetworks, with all of them averaging out to a sort of Occam's razor, where the simplest subnetwork ends up being the most optimal, right? So now this links again to what Professor Min and Alex were talking about earlier, right? With smaller networks, learning superficial patterns and memorization, that is enough. But with big networks and very large data sets, they're forced into true learning. If we look at learning arithmetic as an example. So initially, the subnetwork may wish to try and memorize different combinations and solutions. Now, actually, I don't know, don't quote me on this, but I think I saw an article, a research paper by Professor Min about like how BERT would use heuristics in the text in order to do question answering, as opposed to actually like, understanding it, which by the way is what GPT-2 did as well to some extent. So that's sort of this step here, right? It just tries to shortcut. But with a large data set like Common Crawl, which is like this huge, it's enormous, almost 1 trillion words, it can't possibly memorize them all, right? A subnetwork which attempts to do so will become larger and larger and therefore will be more penalized. It's eventually the most optimal model is one which actually does the arithmetic. And if you look at what the GPT paper says, right, it finds that for its synthetic arithmetic tests, that very few of the problems are actually found in the training set, which therefore indicates that it's actually doing addition or subtraction. And if you look carefully at the mistakes that it made, it's as if it's like, for example, forgetting to carry forward a 1. Right, so I think that about wraps up the discussion of meta learning, but it links to another idea, right? Previously, GPT-2 tried to do this exact same thing, right? If you remember, there are very few differences except for like minor, like for example, modeling after the sparse transformer. There are very few architectural differences between GPT-2 and 3 except for its size, right? And the in-context learning approach, this meta learning approach, didn't work with GPT-2, right? But it started to work as you made the model bigger, right? So I've included this diagram to sort of get a sense of that. So 1.3 billion would be GPT-2, right? Now, by contrast, so this links to this idea of blessings of scale, which essentially means that as you make a model larger and train it on larger data sets, a lot of its problems disappear, right? They become more powerful and human-like. And this all without very complicated architectures. And so the scaling hypothesis, I mentioned this back when I first introduced the GPT paper. Right? The scaling hypothesis regards the blessings of scale as the kind of quote unquote secret of artificial general intelligence. Right? It holds that intelligence is just quote unquote simple neural units and learning algorithms, right? That are trained at currently unreachable skills. And if you look at this figure from the GPT-3 paper, which shows variation loss against compute, right, you can see that as the parameter count increases, right, the validation loss steadily decreases with a power law trend. Right? And I'll leave it to you to decide what that means for the scaling hypothesis. Right. Now, this isn't to say that GPT-3 is perfect. It has a lot of flaws. Right. I think it's, in my opinion, the biggest flaw is that there are no weight updates. And this seems somewhat counterintuitive because no weight updates was supposed to be the whole point. But I think that some forms of learning should be persistent. Right. If I were to, go up to Brian and say, can you tell me how many oinks there are here? He would look quite puzzled and he'd say, what do you mean? It's that ability to respond to nonsensicality, although it can be induced using the in-context learning, it doesn't persist, which is a big limitation. And therefore, it doesn't actually get smarter once the pre-training is completed. Another problem, there's no bidirectional context. I think unlike BERT, this is really a really good thing about BERT is that it can take into account bidirectional context, which suggests that even if the scaling hypothesis is true and all we need to do is scale up very simple architectures, perhaps this is the wrong architecture. And this also explains why it performs so poorly on tasks which require you to compare two sentences. Finally, it's unable to understand languages other than English. Now, I think that this problem is more fundamental than just saying, train it on a French version of Common Crawl, Because when I started learning Mandarin, I wasn't learning it from the level of a baby. Right? I was learning it from the level of a native English speaker, and that meant I could learn it much faster than a baby. And I think this little excerpt kind of encapsulates everything which is broken about GPT-3, at least the very specific dimension of it. right, which is that its inability to learn persistently. So this sort of ties back to that idea of being unable to, reject nonsensicality unless you're instructed to. So we've looked at what GPT is good at. We've looked at what it's bad at, and we've also talked about the scaling hypothesis, meta learning. Now, what does this mean? Right? Like, I thought this would be something which we could discuss. Right? So this is more of a discussion point, right? But like what does this mean? One big obstacle to scaling GPT-3 was the quadratic complexity of the transformer model, right, which limited how big the context window could be. And so they tried to work around that using sparse transformers. But now with, for example, BERT, which I think was presented in one of our previous discussions, that problem's alleviated, right? I mean, I'll leave you with this little graphic here, right? So, well, what's next? What are the implications? If the scaling hypothesis is true, what are the implications for us as NLP researchers for the direction of the field, right, in the short and medium term? I will touch on just one thing, which is the issue of resource availability. If the scaling hypothesis is true, then in order to create artificial general intelligence, we would have to expend a large amount of compute resources in order to scale up our models. And that is not something which is available to the vast majority of institutions, right? Of all the papers we've looked at over the past few weeks, they're not all coming from NUS and Stanford, right? Some of the paper which I found the most interesting, which was one from the last couple of weeks, was from some random Russian university. Right? So if the future of NLP really is just throwing more compute power at a problem and hope it goes away, that means it's limited to a few powerful players. And so this is an idea I talked a little bit about in some research I did, which I'm not gonna, I'm not that shameless. I'm not gonna start talking about it now that much, but I will just note that in comparing BERT and XLNet, which is what I did, XLNet, it excelled on almost all of the tasks which I compared it, on which I compared the two. And yet, the amount of resources which it took in order to train XLNet was huge. Like I had to email Google and ask them to give me free credits because I would not be able to afford to train them on my own. Right? So, on that somewhat dark note, I think I'll conclude my presentation. These are my works consulted. I would really recommend, if you're interested in learning more about GPT, that you have a look at some of these, the papers and some articles I found helpful. But yeah, okay, thank you. That concludes my presentation.
Okay, Khush, thanks very much for your presentation.
Thanks.
So Cheng Lei also wrote in the chat, I think he's observing. He is the primary person who authored the paper that Khush mentioned. He's also like a little bit like Khush. He was a high school student when he started this work. Not even in NUS yet. And he's not going to NUS, he's going over to UMD in the States. But there are a lot of people, I think, at the secondary school level who are getting interested and have exposure to NLP already. And so Khush is one of these individuals who's not at the university yet, but is going to NS. So, one of the other things that I'll note is that, when we think about this as researchers, what Khush is alluding to is a little bit like what you see in the popular press right now, right? Like the concerns that are mounting is that a lot of people are worried about, the training of such language models. Is it really true that all you need is more data? And I think as NLP and ML researchers, we really know that that's not the case. We need to be much smarter with our use of parameters. So you can see the Albert paper is trying to do that as a form of regularization, getting rid of parameters that we don't need. And then even in the GPT-3 paper, I know Samson studied it quite a bit, is that there's a whole section on bias, right? We're quite worried about the use of these language models in production and whether they're going to cause problems. So the interesting thing I think about GPT-3, and please, you guys discuss as well, is that there's not a lot of methodological changes. There are some, and those are important changes. So one change that you'll read in the paper is they changed the context window size to 2K. So that means it has a much larger window of data to look at before it generates. So that means it's going to be able to model coherence and discourse a little bit better than previous models. So you have 2,000 tokens to the left and 1,000 to the left and 1,000 to the right. You're going to get much more than a single sentence, right, as context. So previously, Brian looked at BERT. BERT only had the next sentence prediction task, right? So if you think normal sentences are less than 50 words in length, you're basically squeezing 20 sentences to the left and the right, right? So that's a large difference. Okay, so that's one of the points. Then we can talk a little bit more if you guys have things that you'd like to discuss about this point about not updating the model. So the model is frozen, and GPT-3 is just using few-shot or no-shot to generate the rest of it. So we also talked about CopyNet, right? When we are using source data from the query sequence in order to generate text in our NLP prompt. So that's an interesting use that we didn't learn a little bit before we try to dissect the paper a little bit more.
Hi.
Go ahead.
There was something that struck me in your presentation. I mean, it was a great presentation. First, I want to congratulate you. It was very understandable and nice, nice storytelling. You opened the question whether small research institutions are doomed because in this domain, because it requires humongous resources to make any progress. I want to make the link with your slide where GPT answers nonsense stuff to nonsense questions. And if I were still in academia, what I would like to do is study whether, I mean, this is not a problem with grounding the model. So grounding the model in the sense that humans are grounded in reality, right? So the reason why this makes no sense for us is because we assign a meaning within the real world to each of the vectors that we produce in our head, right? And Spruggle and Morgel don't really, so don't really trigger anything for us. And so if we were to improve this to fix this problem, what we would need to do, right, is to teach to the model a way to know when it doesn't know something, to be humble. I mean, to be grounded in reality and not to try to produce an answer at any cost. But it's if you think about the way humans would do that, it's by just living real life and then being able to differentiate reality from fantasy, and how, I mean, so how I think something that would be worth studying in research that doesn't require scaling to further the trillions of parameters, the size of the model, would be to study how embodying a model in, for instance, in a robotics context or in another multi-model, with different media, how creating a model that doesn't only work within its own NLP world, but within a sort of representation of the real world or within the real world itself through robotics, would be maybe a step towards solving that issue. So that's a very general thought, but that just to highlight that I think not everything is about scaling further, because right? As humans, there is a big difference between the way we would answer those questions or the way GPT answers those questions. So I'm not sure. There are probably actually already research initiatives in that direction. I'm not aware of those things, but
yeah, so that is definitely a good observation, Alex, that you know, there are research groups, many of them actually, looking at grounding. There's good work done at Illinois, MIT, as well as UCSD, UCSB as well, that are all looking at grounded models. So, you know, GPT is only looking at text, so it has no way of learning multimodal representations. We know that humans don't have access to as much text as GPT-3 does. Yet, you know, you and I can learn language very well, and our younger generation is of course exposed to much less text and still can learn very good language models, you know, better than the ones that we have currently. So there's still quite a way to go for that. Yeah. So I think, you know, there's a lot of hype around GPT-3. If you read the paper itself, it doesn't read like a normal academic paper. It has a lot of work on experimentation and not much explanation of the model and its variation. So it's a little bit unsatisfying to read that paper. But I think what we want to also do is study a little bit more about the autoregressive language models, right? So I think our next presenters are also going to talk about that, right, a bit. So I think Ruixi and Jia are going to be looking at parameter efficient learning and transfer learning for sequence tagging with hierarchical recurrent networks. But I'm not sure whether that's the next set of presentations. Is that right?
Yes. I will present. So first, let me share my screen here.
All right, so again, let's thank Khush for his presentation. And again, I think there's a lot to digest from this. I definitely think there's a lot more work that can be done. I think definitely having enough words is, you know, there's always more that you can get with words, more data. But I mean, essentially, even if you have a fraction of the data, but it's at the same level of density for a specific controlled vocabulary, you should still be able to get the same quality output for a model for a constrained domain. Okay, so one of the things is really, you know, if it can perform well on general languages, that's fine. But you know, if you can control the density of the language in a particular area, then can you get to the level of understanding within the model actually doing the work, but also your internal understanding of what the model is doing, like the analysis of why the layers learn what they do, where in the network a certain type of lexical choice or other type of modeling is actually being performed, right? So it's sort of like thinking about neuroscience on the GPT model, right? Because right now, you know, our neuroscientists peers are also trying to study our human cortex, right? Where does decisions get made? And we have to apply the same type of analysis to, you know, a general model that we have coming from very, very simple statistical applications at scale. Okay, so any other comments before we get to the next paper?
I would like to make one small note, if it's okay. Like something Alex mentioned about GPT-3's inability to sort of be grounded in the real world, given that it just functions with text. Like one thing which I'd be interested to see is if, you know, all these various robotics teams in their experimentation with GPT-3 are able to extract some of its knowledge about the world, which like the model itself has inferred from just processing so much raw information, right? Because you have to work pretty hard in order to, or phrase your questions like trickily in order to mess it up. Like in some senses, it's able to like almost fake or feinge like physical intuition. which,
Right.
yeah, anyway. That's just,
And there, I'll just caution again, a lot of what we see out of GPT-3 is just a collocation of statistical information. It really doesn't have any understanding of what it's saying. So this is why in the popular press, we get a lot of flack. You know, people really worried about NLP taking over the world, that GPT can actually compose all these things. These are all statistical regularities that are being captured, and you can use them to generate other text that's similar. But when we say that a natural language system understands primitive concepts like gravity or composition, these are not the case, right? It's not actually learning any of that. It's just learning that basically from other texts, it seems like this is a regularity that I can exploit, and that if I do maximal likelihood as inference, this should be the next token that I spit out. Okay, so that's one of the things we need to really caution the general public when we talk about our own research, because otherwise it does get out of hand. And we see this quite regularly in the press. The problem is sometimes our natural language research community, they're good at math, we are good at math, but we cannot really communicate our findings in a way that limit the propaganda that goes out to the general public, right? Like we see a lot of cases now, AI, when we talk about it, we try to get other people to cite our work. And so the popular press will pick up on those aspects, but forget to mention the really critical limitations of the work. So I think, if you went to ACL this year and, in even past years, a lot of people in the senior science community have started to really worry about this. People are picking up on what a GPT can do, and they're misconstruing what it actually is doing under the hood. There's actually no inference, logical inference, causality, all of these types of things. It doesn't actually understand everything. But it can appear that way, right? Because it's very good at taking up statistical information from a large corpus and representing it well. So that's one of those things that we thought. If you look at the Winograd schema, that's a set of tasks that people thought that NLP systems couldn't do without inference, right? So that's the case where you might see something like the boy couldn't shut the suitcase because it was too big or something like that. And you have to infer what was too big. Is that the suitcase was too big or the object inside of it was too big? So you can switch it around. And those things, GPT-3 is able to do, okay? Able in the sense that statistical regularities from a large corpus allow it to solve it. But again, it has no concept of what it's doing. So these are one of the big cautions that I think senior NLP researchers are very worried about when it comes to talking about research in NLP. Okay, so let's go ahead and have Ruixi and Qing present the other two works. Okay?
Can you hear me?
Yeah.
Okay, sure. So hi everyone. So today I will talk about one papers, the parameter efficient transfer learning for NLP. Next page. Yes. So for commonly used transfer learning techniques are feature-based transfers. So this one is to use the pre-trained real values, embedding vectors, and then feeding to the following tasks. And the second one is the fine-tuning one. So this one is just copying some of the, copying the weights from the pre-trained neural network and turn them in only following tasks. As the Howard in the 2018 work shows that the fine-tuning also often enjoying better accuracy performance than feature-based transfers. So for this work, the adapter-based turnings, it fixes the original neural network parameters and add only a few trainable parameters for each task. So for each new task, it can be added without revisiting previous ones. So on the right-hand side, this just the comparison between the adapters. The orange one is adapter and the blue one is fine-tuning techniques. So as we can see that even with fewer number of the trainable parameters in the adapters, they can still have a similar or constant accuracy result. But for the fine tunings, we have to increase the number of the trainable parameters here. So yeah, so but how does the adapter-based training works? So here we introduce a neural network with a function as the phi here. The W here introduce the parameters inside neural network. For the feature-based transfer, because it uses the result from the embedding of the previous pre-trained models, so we can treat it as a composition of the function chi and with the phi here. For the fine-tuning one, so we adjust the W inside this one. We initialize the pre-trained weights with the similar. We initialize the weights from the pre-trained models and then just to adjust this one for each task. But for the adapter-based trainings, so here we define new function here, which has the psi here. So we have the parameter W and the V. For the W, this is a pre-trained model parameters, and the V here is the new parameters with adding to the models. So it has two features. So firstly, it is a near identity initialization. So we initialize parameters resemble to pre-trained models. And the second is it has a small number of the trainable parameters. So only the V number of the parameters here, it is trainable in following. So here we use a pre-trained model, which is a pre-trained BERT transfers. So before we discuss further, I want to mention some benefit of this one. It prevents, so compared with some other like the multitasks learning or transfer learning techniques, it prevents training. It permits training on tasks sequentially, and it does not require simultaneously access to all data set as the multitask trainings. And also it adds only a few number of the additional parameters per each task. So therefore it saves a lot of memory during the training. Next one. Yes. So here we have a clear close look at the structure of the transfer with the adapter modules. So the left-hand side is a standard architecture transformers. And this one is a transformer with adapter modules. So as we can see, for each transformer layers, we add two adapter modules or layers inside. And these layers has been put after the forward layers and before the layer normalization. So for the adapter layer inside, it has a bottleneck structure. So it has to project high dimensional features into a lower dimensional and then extend back to the same dimensional. And also it has a skip connection to it. So if we initialize all of the weights inside as close to 0, then so this transformer with adapter models is similar to the previous pre-trained models. And also here we consider the total parameters per each adapter layers. So we have 2 times M and D and add D and M. Those two are referred to the bias here. And also during the training, we also consider the layer norm here. So for each transformer layer, we have 2D and that additional 2D parameters to train, and also with the final classify layers. So here I show some of the interesting results in this work. So the first result is a comparison between the adapter and the fine-tuning techniques. As we can see, the orange one is the adapter and the blue one is the fine-tuning. So what we control in the adapter is the size of the units in each adapter layers. So the x-axis is the number of the total trainable parameters for each task. So as we can see that for tasks for the adapters, even with a smaller number of the trainable parameters, we can still have a good accuracy. But for the fine-tuning ones, we have to increase the number of the trainable parameters in order to have a good performance here. And also, we also specifically train only on the layer normalization here. As we can see, we don't have a good result here. And this is the first result. And the second result is the influential, we're trying to find the influential position for the adapter layers. So here the x-axis is the last ablate layers, and the y-axis here is the first ablate layers. So so because those one are just a number of the layers, so we can see what we want to compare or visualize the result here is if we just remove the layer, like if we, so for the cell here, if the first ablate layer is 1 and the last ablate layer is 4 here. So what we're trying to do, what the result here is showing is that if we remove the layer from first to the fourth one, how would the change of the performance look like? So as we can see that so the diagonal shows that if we remove any single layers adapter, it has only small impact on the performance. But if we remove lower layers, which has a, if we remove lower layers here, it will have a smaller impact than the higher layers removed. So similarly on the another task here. So, and I think one of the intuition here is that because the lower layer could extract the lower level features, which could be shared among all of the tasks, while for the higher layers features, it is unique for each task. So we have to, when we remove those higher layers, it will have a larger impact on the performance. And so the third result here is the also trying to extend the adapter architecture here, like adding batch or layer normalization or increase the number of the layers per each adapters and so on. So in all of the cases, the result shows that those are similar to the bottleneck proposed. And at the end, I also want to add some of the one of the similar work, which named as PALS, projected attention layers, which has been done by Strickland. So in this work, it is trained similarly to multitask learnings. So it has a different architecture. Instead of just we add the adapter inside of the transformer, we add the task-specific modules or layers outside of this flow and add it in skip connection way. And the second is the interference, and it might have because when we train these pairs, so this fine tuning require we access to all of tasks at the training time. So interference and forgetting of the store knowledge is possible. And also another work, Sina, perform an empirical comparison between the adapter and pairs. So it shows that her work shows that for question answering on the SWOT dataset, the adapter outperforms other techniques, and also shows that when we freezing the layer normalization inside the BERT, it will negatively affect the performance. So that's all for my today's presentation. Is there any other questions?
Thanks, Ruixi.
Yeah, let's give Ruixi a round of applause for her presentation. Thanks very much. Okay, Yifan, you had something you needed to say?
Yes, so I'm quite interested why this really works. And yeah, so as first, can you talk about some drawbacks of the adaptator based fine tuning? some drawbacks. Can you have some comments on the drawbacks?
Drawbacks, I think, so one of the drawbacks I can think about is because it just adapts a few parameters inside. So I think they might have some limitations for the tasks we can do the transfer learning. So because it just frozen a lot of parameters. So instead of like the technique fine tuning, like the fine tuning, because we have adjust all of the parameters for each task. This one is just inset a new or initialize a new parameters inside. So I think that's one of the limitations for this transfer learning techniques.
Yeah. So because when I read some related papers, I found the performance of the adapter based fine tuning not very good. It seems not the state of the art in some datasets. So I don't know why it really works when compared to existing fine tuning methods. Yeah.
And another thing I'm thinking about is because I can show you here. Yes. So so as we can see that so first just go back to a structure.
Yeah.
So the position we feed we just embed those adapter layers is just after the feed forward layers, and because for the pre-trained BERT transformer models here, we have 12 layers here. So for each transformer layers, we embed such kind of adjustment or adapter layers. So as we can see that for here, the if we remove as we can see here, if we remove the lower layers inside of these models, then it does not affect too much about performance. So it basically says, I think it basically says that if we so for the lower layers models, it's trying to extract some of the lower level information, which is similar for all of the tasks. So those but if we remove the higher levels, then it will affect the performance. So because for the higher level layers, it will summarize some of the information specific to each task. So yeah, I think this one is trying to I'm not sure if this kind of the transformer techniques is trying to do the reduce the memory of the training process for the transformer learnings, because if we can consider that those for the lower level parameters or for the lower level information, we do not train or we don't have to train again for the next tasks. I think it will save a lot of memory for this one.
Okay, thanks for your reply. Yeah.
I have a feeling, I don't quite exactly understand that why adapter works, but my feeling is that it is some kind of knowledge infusion inside the transformer, that given that you are training on a newer task, so you are infusing some new knowledge with this transformer, with these adapters. But why this infusion or why this new knowledge forcing into the model is works, or what is the even they haven't quite like explored the idea that what are the parts of adapters and why these modalities of adapters works, like what sort of activation function or that sort of that why it works. I don't quite exactly understand, because it seems like you are adding new parameters. And given that you are adding new parameters, then as a neural network perspective, it should learn something new with these new parameters. But I have a question. So is it, did they have tried something like froze the whole architecture, but just keep learning on the adapters part. That
yes,
sort of.
yes.
So what's the result
Yes.
on that?
So it froze it froze the pre-trained models parameters, but it is only trainable on the injected parameters, the new parameters, and also it will trainable on the layer normalizations here.
So,
okay, so are we clear about that? So basically the system is that you have a pre-trained model like BERT, you freeze it so it doesn't need to be updated. But during the training of the adapter network, you both inject new parameters that can help you reweight some of the pre-trained model, but you also change the way that the original model was trained so that there are some weights in the original system that can be adapted, right? So you have two basically two sets of controls. You have controls over a part of the pre-trained language model, which you haven't froze. And they have demonstrated it in different parts of the model, right? Not all at the top level, and not at this like sequentially unfreezing, right? I mean, if you look at that fine tuning, usually you envision you let the top levels change a little bit more so that it can adapt to the task. And I think on the heat map that Ruixi showed, it's basically the same idea, right? Is that the upper level parts of the model are the ones adapting to the task. So when you don't have those parts, they start to not work. And the second part is to have all of these new parameters that are being injected into the model to capture other pieces of information that are simply out of the scope of what the pre-trained language model has been able to capture. So Rabio, do you want to go ahead and talk a little bit more?
I got it, yes. So, but it still seems like that we are, the solution is some sort of extending more parameters. So that's now GPT, BART, everywhere we're just extending parameters, and the solution in recent NLP is all about extending the parameters in some extent. So that's kind of like, so can we think of something else here?
Yeah, so I've been thinking about this too. I think the analogy is sort of like putting more horsepower into a car without thinking about other aspects of it. So you look at the number of parameters. We already know from machine learning that you increase the number of parameters, you can overfit a lot, right? So the important thing is when you have a lot more parameters, you have to use them smartly. You have to regularize so your function captures not the intricacies of the training data, but also the test data. Now, this basic type of machine learning knowledge goes out the window to a certain extent because the data set is so large that you know, the nuances or the noise that's induced from training gets washed out in the face of so much data, right? So you have so much data that you know, all the noise is canceling out. So your parameters are mostly going to be able to capture signal. So that is the great thing about having big data, right? Then the other thing is that, you know, if you have more parameters and more horsepower to a car, it doesn't mean that the aerodynamics are less important, right? In fact, they're more important. So I think right now at this stage of NLP, we're at the point where we're just piling as many horses we can get into an engine without really worrying about the other parts, right? Like whether it can steer well, whether it's aerodynamic or gas efficient, right? Because, well, just like I forget Fred Jelinek, who is an old NLP professor from JHU. He has a very famous quote that was attributed to him, but he doesn't remember saying it himself, which is like, every time he fires a linguist, performance goes up. I think some of you have heard that expression. Okay, he was referring to speech recognition. He was a speech recognition scientist at TJ Watson. I met him briefly when I was a PhD student because he did come around to Columbia where I was doing my PhD. I mean, he made this remark when the first wave of statistical NLP came in the 80s. So you know how old I am, right? But the whole point was like, you know, statistical approaches were throwing symbolic ones for a loop. You had more data that was available from digitalized corpora. And so it became obvious to try to exploit all of that statistical regularity. And so, you know, Fred having a lot of linguists on his staff, you know, real or not true, we're never really going to find out. He said that by using simpler and simpler models that can consume more and more data, you could get better performance, right? And sort of like this paradigm is reoccurring right now with GPT-3, right? So Khush presented that, you know, can we swallow all text in the world that anyone or everyone is creating at the same time? So, you know, Google and Microsoft might be capturing your keystrokes as you type in your report to Microsoft Word or in Google Docs, and they're using it to train yet another language model that can do better, right? So is it the case that we can just do that and get away with it? And I don't think that is a very satisfying answer, right? We want to be able to understand language better. We want to pay attention to the, you know, aerodynamics of a car. So we do have to go back and think about, okay, what's the representation that we can use? Can we refine the way we're using horsepower, right? So even though we have all of these models, all of these different techniques that we've covered today are still somewhat in its infancy. I mean, deep learning is not particularly old. It's only about, what, 7-8 years old. So while things have taken off a lot because of the types of algorithms that have come out, we still don't really understand how to apply it effectively. So it's that case that I'm trying to impress with you guys, that the analogy is that we have something that works. We just keep on doing more of it until it breaks, sort of like Moore's law. And when that paradigm runs out, then we have to think about a new solution to that, right? So, you know, there are lots of things that we can do in natural language to try to get better performance. That's not just about scaling up. So you can see a lot of the efforts are in scaling down, right? So can we get rid of parameters that are not being used? Okay, so if there's part of the language model that's not being accessed at all, can we throw it away without penalty? Are there parts of the model that we can allow a little bit of fluctuation or a lot of fluctuation? The reason for, again, freezing parameters is that you don't need any computation, right? Like fine tuning, you have to update, so it costs effort to do that. Right, and so GPT-3 said, you know, forget about all of the updates. You know, you don't have to do anything. You just freeze the thing as it is and use it straight out of the box, right? But you know, as we get more advanced and we have good enough understanding, I'm sure you'll see more models start to look at the other things. I mean, you don't want a Lamborghini or a Ferrari to have a huge engine block sticking out. It just look like unsightly and it wouldn't make any sense, right? So you still have to go back and think about, okay, all of these parameters that we stuck in the model, all of these texts that we've got, is there a way to use that more effectively, regularize more effectively, learn representations that are more robust to whatever we want it to do, right? So maybe we don't want it to capture bias, we don't want it to capture gender, statistical patterns that encapsulate gender bias, those types of things. We can engineer controls, but we have to be able to do that by understanding what is in the model that's capturing it in the first place. Otherwise, we have no way of fine tuning, right? So I think that's one of the things that you will see in the next few years in natural language processing is, you know, both what Alex said earlier about being able to use multimodal information, because text, as we know, is ubiquitous. It carries the most signal that we have out of all of the digital modalities that we express information from. But certainly now we have a lot of other ways of capturing and transmitting information, like video and images, right? And there'll be other things in the future, like three-dimensional representations. So all of those will go into such understanding models. And I think a lot of NLP groups, including my own, through a couple of researchers in our group, are also looking at those dimensions. Yeah. Okay. Do we have other questions and discussion that we'd like to do? Because I've just sucked up another 10 minutes ranting about the future of NLP research, and also giving you a little bit of storytelling about the old wave of NLP. So I hope that's of interest to you, you know, that the same type of paradigm shift that you're observing today, you know, very data hungry, was observed by researchers at the very, not at the beginning, at the middle stage of NLP, you know, in the 80s, right?
I guess I can quickly go through like the last two papers. Yeah, so.
Okay, Judging.
Let me just share my screen. Yeah.
Thanks.
All right. So I mean, it's two papers. One paper from 2016, I mean, archive paper, preprint 2016, ICR 2017, more is just a baseline. So I'll just quickly briefly go through this as a baseline for the second paper, which is a ACL 2020 paper on low resource sequence tagging using a sentence reconstruction. So for this paper, which was used as the baseline for the 2020 paper, I think the novel contributions at that time, I mean, they might not be novel anymore right now, but I mean, at that time, one was the transferability of different layers of representations. And the second one being that it was trying to create a framework for a unified framework where different permutations of how you use the different levels of layers of representation can be used for different kinds of like for the cross-application task scenario, the cross-lingual scenario, and the cross-domain transfer. So here are the different like permutations of the framework. The base model is one where character embeddings are fed into a character layer, and from this character level layer, it encodes the morphological represent information at that character layer, and then word embeddings are fed together with the character embeddings into a word level layer that combines those two feature represents together, and then outputs a new feature representation into a CRF, and the CRF is what then eventually creates your sequence labels. So we have a few different permutations of how this can be then adapted for different scenarios. So one would be the cross-domain transfer kind of scenario, where firstly, if you have a cross-domain transfer where label mapping is possible, that's where they use transfer model TA, which is the one that I'm pointing to. So the label mappings are mappable, so you can still use the same CRF output of the label sequences, but you just have a further step of just mapping what the labels are. If the cross-domain transfer does not have mappable labels, then meaning that the label sets are disparate, then they need to break it off at the CRF layer, which is transfer model TD. And then we also consider the scenario of cross-application transfer. Cross-domain is where you have like sub-languages, like very domain-specific kind of languages. Cross-application is a different like application that you are, a different application task that you are dealing with. So with a different application task, if you assuming that it's multiple applications in the same language, then you can use this transfer model TD as well, where the representations from this word neural network can be fed to different CRFs to create different label sequences. And then the last scenario is transfer model TC, and this can be used in, for example, cross-lingual transfer. Like, because if you think about Spanish and English words, for the same word, sometimes, both Spanish and English have the same characters. But this, maybe at the word level, there are some slight differences. So you can still share the character embeddings and the outputs of the character level network. But then at the word level, because there are differences, then you break off at the word level. So these are the different permutations within the framework of how this cross-domain, cross-lingual, or cross-application can be used. And another interesting thing about this paper was that it introduced that idea of joint training for two tasks, meaning that so this is the procedure for that joint training. First, you sample a task based on a binomial distribution. Is it the source task or the target task? And then given the sampled task, you sample a batch of training instances, and then you do a gradient update to both, according to the loss function, but update both the shared parameters and the task-specific parameters for the source task and the target task. And then you repeat this, but you stop at so there's this thing to note about early stopping on the target performance because of the different convergence rates between the source and target tasks. And I mean, understandably, if it's the gradient updates are according to the source task, then perhaps the convergence might happen. I mean, at least at local minima faster at the target task than the source task, which is why we do the early stopping of the target task performance. So that brings us to the second paper on low resource sequence tagging. So the baseline that was used in this paper was the same as the one in the previous paper. But for this paper, the main idea that it's trying to put forth is that of the reconstruction loss. So I mean, by 2020 ACL, things like all this about all the things about the previous paper are really well established. They also, in between the two papers, there also came up this idea of the adversarial loss, which I'll explain later in further detail as well. And then, but the main contribution of this paper was about the reconstruction loss. So, I mean, by this time in ACL 2020, the idea of using encoders, decoders was pretty well established as well. So that idea of that adversarial loss is that you have this discriminator convolutional neural network so essentially what it does is using the sentence representation, you feed that feature vector into a discriminator CNN, which tries to tell. Okay, so before I realize I have to explain that this was focused on cross-lingual. So the discriminator CNN was would be trying to discriminate and then discriminate between that two different to predict between two different languages. So they add a switch layer in the input that arbitrates between feeding sentences into the discriminator from the source or from the target language, and the discriminator is trained on normalized hidden representations generated by each sentence, and then it outputs possible labels on whether it's for language I or language J. And then your generator will try to fool that discriminator and cause it to predict the opposite. And this is how the adversarial training happens for this particular branch of this network, of this architecture. As for the reconstruction loss, essentially what it's doing is that so the reason why you have the reconstruction loss is because so the reason why you have the reconstruction loss is because the adversarial loss does not necessarily kind of enforce that it needs to learn meaningful sentence representations. So what you are trying to do here with the reconstruction loss is that you are forcing it the model to learn how to reconstruct from the hidden representations back into what the input tokens were. That's why you see this loss function over here, where it's taking the sentence, the feature representation of the input tokens, as well as the input tokens in the input sentence, and the hidden representation of what the decoder is predicting to be the input sequence, and then you take the loss from there. So this is an L2 loss, and so yeah. So one more thing to note is that it's important to normalize the representing vectors of this of the sentences because this loss is essentially comparing the similarity between the input sequence and the decoded sequence that is trying to predict what the input sentence was. So essentially, the whole intuition or idea is that you're forcing the hidden representations to kind of encapsulate more meaning of what the input sentence sequence was. Yeah, so this is the what I was talking about for the limitation of the adversarial training scheme and what this sentence reconstruction loss is trying to address. So we look at the results. What was interesting to me was that, and also pointed out by the papers, this marginal difference between when you have the adversarial loss included and when it was just the normal weight sharing transfer learning and with the sentence reconstruction loss. So if you compare between this column over here and this column, actually, there are quite marginal differences. And that was interesting. And I mean, that's perhaps a question for discussion about why perhaps adding the adversarial loss didn't make that much of a big difference in performance. And then these are the results for the 2017 paper, which is the first paper I discussed. And another point about this paper is the strength in few shot and one shot learning. I mean, some of this baseline is just the pure baseline from the, I think it's Lampel. Yeah, the Lampel 2016 paper, which is just an LSTM on character tokens concatenated into the word embeddings and then running an additional LSTM. So you get 0 F1 scores for that. So I don't think that was very fair in terms of this presenting these results. But I mean, one point about the paper was its strength in few shot and one shot learning as well. Yeah, so, and that's the end of my presentation.
Okay, thanks, Jiaqing, for your presentation. Any questions about Jiaqing's presentation? Let's give him a hand first. So that's a tall order, presenting 2 ACL papers and ICLR papers in under 15 minutes or less. So hats off to you. Good job. So other comments?
Yeah, Jiaqing, I have a question. Why this method can help to handle the zero shot classification problem? I don't think these three modules, like the classification loss, the adversary loss, and the reconstruction loss, can help us to do that. I don't think they have some connections. Yeah, so why it works?
You mean specifically for the few shot and one shot?
Zero shot.
Or zero shot as well.
Yeah.
Yeah. That I. So that I don't have a really answer for actually.
How about the rest of you? Do you guys want to chime in with any information that you're able to get from the paper or your own knowledge?
Yeah.
Anyone want to take a shot? So, you know, this paper introduces an adversarial loss as well as a reconstruction loss. Abhinav's mic is not working, but if you have anything to add, maybe you can also put it in the chat or on Slack. Either way is fine. So Abhinav writes, you know, it learns a language independent representation. Yeah, so with any zero shot method, right, it has to rely on whatever is already in the trained model in order to give output. So definitely it needs that to do any work on the zero shot learning aspect, right? And I think the key part is what Jiaqing presented, sorry, in 3.3 and 3.4 in the paper about the difference between an adversarial and a reconstruction loss, right? So the adversarial loss helps to get the system better, but at some point it just knows how to be an adversary and doesn't necessarily represent the original data anymore. So they have added this second reconstruction loss. And for those of you who can remember, you know, in vision papers as well, you have a residual loss. So that's another terminology that you may recall from residual networks, right? So you basically take whatever information that is not captured from a previous layer and propagate that up as something that needs to be captured at an additional higher order level. So, you know, you can think about how these terms relate to each other, the residual loss and the reconstruction loss. You know, if you add all the residual layers together, do you get back a reconstruction loss, for example? Okay, so the adversarial loss is more related, I guess, again, to the simple idea of a GAN, right? And so anytime you have a GAN type framework where you're generating an adversary, you have to be able to first get an adversary that's worthy of training against. So there's a lot of instability in GAN training due to that as well. They didn't talk about it much in this paper.
Okay, thanks.
Okay, any other comments? Yeah, I know we're a little bit over time. It's 3:10 now, so I think we're going to go. So let's thank all of our presenters today. We went over quite a lot in the last week on domain adaptation from a theoretical point of view, and now a little bit more from the adaptation point of view to actually using very large pre-trained language models. So next week we have a new topic, but it's also the case that for all of you who are external and 6101 CS students, you will need to put together your abstract for your project. So I hope you have been actually working on your project, because of course, we know the second half of the semester gets very busy. And for those of you who are in the first week, so I think there are only a few of us who are 6101 PhD students in the first part of the lab rotation. Next week is your last required week to join the reading group, although of course we invite you to continue on with that, and we'll be welcoming another cohort of students who haven't joined us yet, who will be taking up more duties in the second half. Okay, with that, I think that's all we should go over today. So again, thanks to all of you. For those of you who were in week recess this week, please help to get the Scribe document and all of the other artifacts from this meeting under wraps so that we can conclude all of the work from this week. Okay, so thanks everyone. We'll see you next week on Friday again.
Thanks, Prof.
Thank you. Take care, everyone.